Okay. Can you hear or see anything? Oh. This might be working. Can you hear me? Is my audio coming through? Oh, awesome. People can hear me, sounds like. Awesome. So we can get started. Sorry about the delay. This streaming thing is new for me, but go into present mode. Alright, so I was going to wait for people to show up, but since it's significantly past 11, we'll just get started. My notes. I seem to have lost all of my notes. Sorry about that. Anyway, so my name is Alyssa Batula, and I'm an electrical engineer turned Python developer. I got into machine learning in graduate school, and I'm super excited to share it with people. So I start off, I think I've mentioned this many times, but we have oops, don't go forward yet. The notebooks I'm going to be using for the code part of this course are available online. So I'll just start with a presentation on a brief introduction to what machine learning is and what you can do with it, and then I'll start going over some actual code. How would you work with this in Python? I'm going to keep most of the code kind of high level, talk about the machine learning parts, but the specific code, it's available in the notebooks if you want to go back and look at it later. So let's get started. So first of all, what is machine learning? So I really like this kind of funny clip that I found online about, different people's perceptions of machine learning and what it is and what you can do with it. So the most interesting ones to me are kind of the bottom row. A lot of programmers think people who do machine learning do lots of math, solving complex equations maybe even by hand all day. And, you can make really cool graphs and play with data. It looks kind of matrixy, but really what I do most of the time is from scikit-learn import whatever model I'm going to be using, and then predict it and train it. So getting started with it is a lot simpler than a lot of people think. And, right, so I really kind of like this definition of machine learning. It's an area that gives computers the ability to learn without explicitly programming them. So instead of saying, in this scenario, do this, in that scenario, do that, having explicit steps of what the computer should do in certain situations, you give it a lot of information and tell it to learn from that information. It's somewhat modeling the human brain, how people think and learn. When you're a kid, people give you examples of something like, this is a dog, this is a cow, and slowly as you see more and more examples of dog and a cow, you can start to tell the difference between the two. They both have 4 legs, but a dog is smaller, they make different sounds, all of these different things. So we're trying to do a similar thing with computers, just give them the information and have them learn. Who uses machine learning? Just about everybody. Amazon, trying to predict, what other things you might want to buy based on things you've already bought. Pandora is trying to predict what songs you might want to listen to based on songs that you've had before. Facebook, how it chooses what's in your newsfeed. And then Google, of course, all of your Google searches and predictions about what you might be interested in reading. So what kind of problems can machine learning solve? There's 3 main categories. There's classification, where you predict a category. Is something a cat, a dog, a cow? There's regression, where you're trying to predict a quantity or a number. What's the price of this house? How large is something? And then there's clustering, where you're grouping similar things together rather than trying to assign a label to it. And so classification and regression are something called supervised learning. This means that we have a target or a label, something that we want to predict, and we have information that already has that. So for example, if we have a bunch of houses and we want to predict the list price of the house, we could have information on, many previous houses and what they sold for, and that house price would be our label. Whereas with clustering, we might not have any kind of label, but we still want to learn about it. So for example, if you take a bunch of pictures off your camera, just download them and you want to find maybe similarities between them, but you've never labeled them. You've never gone through and said, this is a picture of me, this is a picture of my cat, this is my grandmother. You just have the computer try and find similarities without telling it anything about the data. So how do you start with machine learning? So the first step is you want to gather and clean your data. You need to have some information to work with. You want to decide how to present the data to the algorithm. For example, we have a question. Yes, we should be live streaming. And it should be at the link that was tweeted out. I can just copy and paste it too. Okay, so the link is in the comments chat, and just a reminder, like anytime you have any questions, I'll try and keep an eye on it. This is much more fun when people ask questions and I get to answer them instead of just feeling like I'm talking to myself. Alright, so the next thing, so you want to gather and clean your data. You have to have the data to give to the computer. And you want to decide how you present it to the computer. Like, what information is most useful? What do you want to give it? So, housing price is an example again. Things like, the neighborhood, the number of bedrooms, the number of bathrooms are all useful information you might want to include. Then you want to select your machine learning model. What are you going to use to try and predict? And there's a lot of information on the internet about how you might make your first choices there. And then the last thing you would do is once you've trained your model, you would train your model, and then the last thing you would do is evaluate your model. There we go. So we're not going to talk about this too much today. We're going to focus on the machine learning, but I wanted to point out that your data is responsible for how well your model performs. So an really important question is, does your data set accurately represent what you're trying to predict? Is the information that you need to make good decisions actually in your data set? There's a common saying called garbage in, garbage out. If your data is not good or it's not organized in a way that the computer can understand, your model's also not going to be very good. So while we're focusing on the machine learning part of it today, that is an important consideration before you get started, is making sure that your data is in a nice clean format and everything is accurate, so you're not giving false or misleading information to your algorithm. As I mentioned, there are ways of selecting a model. Scikit-learn is the library that we'll be using. They have a lot of great information. They have, including this algorithm cheat sheet. And you can follow along, do you have enough data? Are you trying to predict a category? And you can follow this this little chart to try and figure out what algorithm you might want to try first. This doesn't mean this is the only thing that might work. You could try many different similar things, but this is a good starting point. Alright, so now we're going to go into the notebook examples, and I knew I was going to forget to update a slide. So we'll just move on over to those. So I have this running in Jupyter Notebooks, and we're going to get into the actual code of this. If you're following along, I'm going to start with the diabetes dataset one. Alright, so I've talked a little bit about this before. There is, so your dataset is what you're going to give to the computer. It has your features and all this information. And just to define this commonly used terminology a little more. So an example is a single element of your data set. So, for example, a particular house. It's usually a row if you're having... Oh. So we have a question, where do hard rules come in? I see some places saying that is also machine learning, But whenever I see myself coding rules to classify something, it seems to be a bit of computer learning without me coding into it. Sorry about that airplane, if that came through my microphone. So, I'm not entirely sure I understand the question. So, I think the question is the difference between hard rules, like the computer's hard-coded to do something, versus machine learning, is that right? But, so that last part, the computer, okay. So, this is, I guess, kind of a highly debatable topic. So, artificial intelligence and computers being intelligent, or acting intelligently, is kind of a wide and messy field, and people are going to categorize things in different ways that make the most, there's a lot of disagreement. But one of the ways that I like to think of it is kind of artificial intelligence is anything where the computer is acting intelligently, or at least something that we could perceive that it's making intelligent decisions. So the very earliest version of that was this simple rule-based method where the rules made the computer seem smart. Like old school video games, those very simple controls that had the the video game opponents act somewhat intelligently was kind of our first steps. But machine learning is kind of a subset of artificial intelligence, where we're actually having the computer learn from the data instead of doing that step-by-step rule-based faking intelligence. Is that okay? Awesome. Glad I answered that. Where was I? Okay. So an example is a single element of your data set, basically a row, and that would have, information about that one particular element, like an individual house. And then the columns would be what we call features. So it's some kind of measurable characteristic about this example. So for a house, it might be the number of rooms, the number of bathrooms, things like that. And so these examples and these features are what make up, this data set that we're giving to the computer. And then the last bit is, I mentioned earlier about a label. It's also sometimes called a target. So this is that identifying piece of information that we want the computer to learn about. It's what we're most interested in. So as I mentioned earlier, the house prices might be a label, whereas the number of rooms would be a feature. So we're going to start out using, there's a diabetes data set that's available through scikit-learn. And it has information on specific patients. So each patient is going to be a row, a single example. We have 442 patients. And our features, there are 10 of them. There's the age, sex, body mass index, average blood pressure, and then 6 different blood serum measurements. And then our target is a quantitative measure of how much the disease has progressed after 1 year. And so for our example here, we're going to look at this data set and try to train a computer to predict the progression of diabetes after 1 year. So now we finally get to the code. So a lot of the code in these notebooks is pretty plotting. But some of the important ones here are from scikit-learn, we're importing datasets so that we can get our dataset. And yes, for now everything else is just plotting. So if we run this, and then we want to actually import the dataset. So we're loading in our dataset, storing it to a variable diabetes, and then we're going to list some information. Yeah. So let's take a look at this. So when we load the dataset in, it's essentially a dictionary. It's not quite a dictionary, but very similar. And it has the keys data, target, this description, and feature names. And then the feature names are what I mentioned earlier, age, sex, BMI, and blood pressure, and so on. And then if you just plot the first 5 examples, you get an array of numbers. So this is all the information for the first 5 people. But this is not the most intuitive way to look at data, so we might want to visualize it. So we're going to make a scatter plot. And so we have this normalization is just because the target values are between 0 and 1, we want to make the plot look a little prettier. Then we do a scatter map with a color bar, and we are plotting serum measurement 1 against serum measurement 6. And so this is what that data looks like. You can, of course, make your own plot. So if you want to do a little bit of live coding here, so we've just looked at 2 different features, but there's 10 features in this data set, and we might want to know how they're all related. So we can copy all of this down into here, and feel free to follow along. This is actually intended to be a workshop, so if we do this, and let's say we want to look at, this should be serum measurement 2, and this should be 5, assuming that I'm getting my indices right. So change that around. And we get a somewhat similar looking cluster, but it's a little different. But so this is one way that you can go through a data set and kind of look at the relationships. A link to the notebook. Yes, I do. It is further up in the chat, but I will just repaste. Oh, thank you. Someone already posted it. Alright, so that's a little bit on data visualization, and there's a lot of information out there if you want to learn more. There are methods for taking things with 10 features and trying to visualize them in only 2 or 3, because that is rather difficult. But for right now, that's about as far as we're going to go into visualization. One more thing I want to talk about before we get into the actual algorithms is the idea of training and testing sets. So we want to build these algorithms, but we also want to know how well they work. So to do that, we're going to divide our data up into 2 or 3 different sets. So we have a training set, and this is the portion of the data that we're going to use to train our algorithm. We're going to give it to the computer and say, learn from this data. So this is usually a big chunk of our data set because we want to give it a lot of information to learn on. Then there's the testing set, which is a smaller portion of the data set. We don't give it to learn from it. We don't let it see that data, but we then have it predict based on that data. And because we have the labels, we can see how much of it we got right. And I'll go a little more into exactly how we do that in the future. The third one is called a validation set, which is somewhat optional. But a lot of the times we're going to want to choose between multiple different models. Does, using this algorithm or this other algorithm work better? And for that, we would use what's called a validation set. So you can think of these as kind of, in schoolwork terms, the training set is your homework. This is how you learn. This is how you learn the topic. Your validation set is like a practice exam. It's not the final test, but it's to gauge about how well you would do on the problem. And then the testing set is your final exam. This is where you see this algorithm does work well or this algorithm does not work well. So scikit-learn makes it pretty easy for us to split our data set like this. So there's a function called train test split. We give it our data x, our labels y, and we tell it what percentage, how big we want our test size to be. So here we're doing 30%. And then it's going to give you back your training and testing features and your training and testing labels. So if we run this, we can see that in all cases we always have 10 features, but we start with a data set of 442, and then we wind up with a training set of 309 and a test set of 133 examples. So this is great, and this is how we evaluate. But especially when we use all 3, training, testing, and validation, we're splitting up our data set smaller and smaller. And while we want to make sure we always have this kind of fresh, unseen data to test on, we also want to use as much of our data as possible in training. So one way we can do that is something called cross-validation. So what we're doing is we take our, here we take our training set and we divide it into, say, 5 different chunks. And so we go through, and each time we hold out one of those chunks to use as our validation set, and the other 4 we use for training. We see how well our algorithm does on that, and then we repeat that holding out a different chunk. And so then we get 5 measures of accuracy, and we'll usually take the average of that to see which of our algorithms we're comparing works the best. And so, again, when we have an actual model to work with, I'll show you an example of exactly how that's done. But for right now, to set up the folds, scikit-learn again has something called kfold. If you have an older version of scikit-learn, it might use something called n-folds instead of n-splits, but other than that it works the same. We tell it that we want to use 5 different folds, and we use an iterator. We tell it we want to split our training set, and then it will give us training indices and validation indices. So train test split would actually split the data for us and return our individual data sets. This one just gives us indices, so we have to split our training and our validation tasks and labels separately. But we can run that and see that we wind up with 4 folds of 247 examples and 1 of 248, because they're not entirely equal. And so there's also more information on different ways you can use these training and testing sets. Scikit-learn has some great information. There's a link in this. So before I move on, are there any questions? I want to just make sure that we're all on the same page before I move on to the actual algorithm. There's also a great chance for me to grab a drink of water. Okay, so I'll keep an eye for more questions, but we're going to be moving on. We are next going to do I wrote this down, linear regression. So the file. Oh, sure. So we have a question. Could you please explain the underfitting concept? So while I'm at it, I'll go for both underfitting and overfitting. So we have these models, and we are trying to get this model to accurately describe or predict our data. 2 ways we can go wrong is underfitting and overfitting. So I'll start with overfitting. Overfitting is when your model is too powerful for the data you have. So it can model essentially noise in your data set. So sticking with the housing example because it's easiest for me to visualize, but if you have a very powerful algorithm, it could start to, not just generalize things like the number, if there's more bedrooms, the house is probably going to be more expensive. It might start trying to memorize things like this, this particular house had this many bedrooms and, this many bathrooms. And it might start memorizing individual examples instead of generalizing to, more bedrooms, more expensive, nicer neighborhood, more expensive. And so the opposite of that is underfitting, where your model isn't powerful enough to actually model your data. So you might have a lot of complexities in your data. The price of the house is dependent on, the number of bedrooms, but also the number of bathrooms. But if it's not in a good neighborhood, it doesn't matter how big the house is, it's not going to sell for as much. And if your model is too simple, it won't be able to model all 3 of those things together, and it'll be too simple of a prediction. So one way to visualize this is if you've ever done anything, I think I did this in high school, but if you're fitting a line and sometimes it's a straight line across and you can fit it with a line, but sometimes there's a curve or parabola and a line wouldn't be able to fit that. So it's that kind of matching the complexity of your problem to the complexity of your algorithm. That was a really good question. I forgot to go over that. Alright, and if there are no more questions, we will go on to linear regression. As this loads up. Awesome, great. So, linear regression is an algorithm where you're trying to predict a number. So this is great for our diabetes dataset because what we want to predict, the progression of disease, is a continuous value. And it's very similar, well, regression is essentially that line of best fit that you can use in Excel if you have a lot of data and have it fit to that you've already done linear regression if you've ever asked Excel to fit a line to your data. So now we're going to teach you how to do that in Python and perhaps with a little more complicated data. So setup, numpy and matplotlib for plotting. In addition to datasets, from scikit-learn we want the linear model. We have our train test split and k-fold. And scikit-learn also has metrics, which we'll talk a little bit more later, but these are ways that you can evaluate your model and see how well it's doing. So for linear regression, we're going to look at the mean squared error and the R-squared score, which we'll talk about later. Yes. Okay, so I won't spend too much time on the data set because we just talked about it, but you can get kind of a description of it. It tells you a little bit more about it. We want to create our training and testing sets. And we've got a little more data visualization. This time we're plotting the body mass index over disease progression. And so for this small initial example, this is mostly what we're looking at. How well does body mass index predict the progression of the disease over the course of a year? So we'll start with a toy model. And so a toy model just means that we've simplified something for the sake of example. So we have 10 features, but we're only looking at one just because it's much easier to make these plots that way. So the first thing we do is we want to create an object for our model. So linear model has a linear regression object. So we store that in regr, which makes more sense if you're typing it, not speaking it out loud. This is just a reshaping that we have to do because we only want to use one feature, so we get that feature. But then we have to reshape it because a regression model is going to expect a column vector with, examples are the rows and features are the columns, but Python likes to get rid of columns if you only have one and turn it into just a single row vector. So we get our training data, and then we're going to fit the classifier. So when I talked earlier about training a classifier, this is what that fit function does. We have our model, we tell it to fit, and then we give it our features and our labels that we want it to learn. So we run that, and it says that we have a linear regression object and various parameters about number of jobs and normalizing that we don't need to deal with today. So now that we've trained it, we want to make some predictions. And so when we do that, we would use the predict method. It's going to expect a single input. So here we have the predictions we're going to give it. So we're going to give it 2 predictions because we trained it. So each row here, it's probably easier to see actually if I do this. So each row is going to be our number that we want to give it to predict. And then the method to call is simply predict, and we give it our data, and it will give us a prediction. So for these 2 randomly selected BMI entries, its predictions are 103 and 251. But once again, visualizations are often much easier than just looking at numbers like this. So we want to create a scatter plot. And let's just go ahead and make this. Alright, so what we're doing here is we are plotting our 2 features. So this is the body mass index versus disease progression again. But on top of this, we're plotting that line of best fit that we talked about earlier. So here we make that scatter plot, and then we get a range of values that we want a range of values that we use to make the line. So we want it to go from -0.1 to 0.15 and in steps of 0.01. So this is just making a line. And then we have our nicely trained model predict the output for those values, and then we plot it. And so that's how we get this line right here. Was that clear? Is everyone following me what we just did here? So we plotted our data, and then on top of that, we just plotted the predictions that our algorithm would make. Okay, so now we have this model, and we've plotted, you know, where does the measure of disease progression come from? That is an excellent question, and I myself am not entirely sure. It is, let's see, what is the official here? Yes, so the second question, which I can answer first, is the red line shows the predictions from the algorithm, correct? And yes, that is true. Where is it? Okay, so it says our target is a quantitative measure of disease progression 1 year after their baseline measurements. So this is something that, some quantitative measure that medical professionals have come up with to try and quantify how much the disease has progressed. And so it doesn't provide information on exactly what that is. But that is an excellent question. And if you really wanted to work with this data set, you would want to dig into what exactly that means, because it could influence how you choose a model and how you work with this data. So that is a really good question. And then going back here. Okay, and so just again, yes, the red line is showing, for each value of body mass index, this red line is showing what our algorithm would predict for that value. And then we have another question, why did we start from -0.10? So I started there, so I was trying to pick values that spanned the entire data set. So I just kind of visually saw that it went down to almost -0.10, and it went a little past 0.15, but that's how I picked the endpoints. Oh, I think, so there's another comment, I guess if you are too thin, your BMI is negative. So one good thing to point out that I forgot to mention is this data has been normalized. So this isn't your actual BMI, because you're right, it's usually a number, a positive number. So what they did is they normalized the data, so if you subtract the mean from your data set, and you'll usually divide by a standard deviation. It's nice for visualizing. It gets all of your features to be kind of centered around 0, and so you don't have to worry about things like, you know, BMI is numbers in the 20s, blood serum levels might be, you know, tenths of a point, but if you want to look at them together, it's nice to have them on the same scale when you're analyzing them. Alright, great. So now that we have this model trained, we want to test the ability of this model to actually... Oh, one more question. So you chose your X range to include as much of your data set as possible. Yes. So that was really just for plotting. So that was the range that I wanted it to draw that line for and show what it would predict. But it's not something you'd usually have to specify for actually training the model. It's just the range of values that I wanted to see what the model would do. So I could just say, you know, -0.5, and let's go up to 0.5. So I could do that, but now, you know, it's giving me predictions for numbers that I'm maybe not interested in, and it's harder to see my data set because it's all kind of scrunched up in the middle. So that's just why I picked those numbers. I wanted to see what that line would look like on the areas where we do have information. Alright, so we are testing this toy model, and so we've already trained it, but we want to not just test it on fake data, we want to see how well it performs based on this testing set that we've held out. So the first thing we want to do is, because we trained it on only one feature, we can only test it with one feature. So we get just this one index from our test. And then we get our predictions. We give it our testing data and ask it to make predictions. And then we are making a scatter plot. So this time we are plotting our test data and its predictions. So this is our headout test data, and you can see that our test data is smaller, so there's a lot fewer dots present than when there was in our training data. And then here's our regression line, and you can see it still seems, there seems to be a positive trend, it still seems to fit with the test data as well. But that's very qualitative. I can say, oh, that line looks like it fits pretty well. Someone else could come along and say, no, not really. There's a lot of points pretty far from that line. Someone else might feel that it doesn't fit very well. So what we want is a numerical way of evaluating how well this fits, instead of, a qualitative description. So one thing we can look at is the mean squared error. And so scikit-learn has a super easy way of doing this for you. But essentially what it is we are taking, scroll back up, for each point, the distance between that point and the line, of prediction. So for each point, we take that distance, we square it because we're not interested in negative numbers, and so squaring gets rid of negative numbers because we don't want, a positive error and negative error to cancel out. And it also, the further away you are, because you're squaring it, you're being penalized more heavily. So something like this point way up here would have a higher penalty because it's way off, whereas this is still pretty close, so it would have a much smaller penalty. So for each point, we take the distance between it and the line that would predict it, we square that, and then we add all that together. And so that would be squared error, and then the mean squared error is we just take the average value of that for all of our samples. So we run that, and we get a mean squared error of 3,833.3. That's nice, but what does that really mean? It doesn't mean anything really outright. You can't look at that and necessarily say, oh, that's really good, or oh, that's really bad. In general, a smaller one is better. But just looking at this number, I can't tell if this is a model we'd want to use or not. So there's another metric we can look at. This is called the Rsquared score. And you may have already seen this, so if you ever fit a line to data in Excel, it'll usually give you this little Rsquared score. And so it's a measurement of how well this model predicts the data. So if your value is 1, it's a perfect predictor. Every single point falls on that line. If you get a 0, that means there's no correlation between the input and output. Oh, awesome question. Someone says, I get 3,600 and some other numbers. They don't think they changed anything. Where does that difference come from? It actually makes perfect sense that you would get a different value. So when we split our data into a training and testing set, NumPy does that randomly. And so the exact examples that wind up in your training and testing set are based on how it randomly does it. So if I ran this again, so let's see if we can remember, where did we find that? Right, so mine is 3833, but if I divide my data again, it's going to be way near the top. Yeah, divide my data again. So now mine is a lot higher. Yeah, and so this is another thing that's kind of important to consider, is that the smaller your data set is, the more likely you are to see things like this. Because if you're not depending on how your data is split, it's going to affect your accuracy. So that's another nice thing about that, that fold method I talked about earlier, and that because you are looping through your data and looking at different validation sets, and you're kind of getting an average value instead of just one number based on how it was partitioned. And we have another question. So positive errors are above the line, negative are below the line. But we want to know the amount of error in either direction, so we square them to cancel the negatives, correct? Yes. Yes. You could also do an absolute value instead of squaring them. It would be a different error metric. But yeah, we also like squaring because it's getting rid of that to cancel out the negatives. Alright, and so there is, oh, that's right, I have to rerun everything now because I changed stuff. Alright, so just run this one more time. Yeah, and so if you ever do something like you change the way something's split in a notebook, you have to make sure you remember to go and run it all over again. Okay. So now that everything makes sense, all of our data is correct again. So we have this Rsquared score metric. We give it our test values. So the y-test is the actual labels, and then we also give it our predictions. And then we get an R-squared score of 0.32. So it's, it's okay. It's not that great. But we're only looking at one feature right now. What if we train them, and that feature doesn't even have anything to do with these blood serum levels? And, I don't know a lot about diabetes, but I know it's very important for them to be constantly checking their blood measurements. So it would make sense that we might get a better model if we would start including that. So we want to train a model on all of our features. That's very similar to before. We get a regression model. We do the same fit function, except we give it our entire training set with all of its features. We ask it to predict, and then we get the mean squared error and the R-squared score. But what if we wanted to compare? So, looking at it right now, it did get a higher R-squared score, which tells us it's better. But if we really want to compare the two, we have to use our validation set. So as mentioned before, this concept of overfitting, there's a lot of hidden ways to accidentally overfit on your data set. And one of them is to train a bunch of models, test them all on your testing set, and then pick the best one and say, this is my best one, and this is its accuracy. The problem with that is that you haven't necessarily picked the data set that works the best on this type of data. You might have just picked the data set that works the best on your test set. So adding that validation data, that practice exam, is a way of, it allows you to pick your data set based on the validation data, the practice exam. And then when your final evaluation, you do just on the test set. And so we'll go over that in a little more detail. It's probably going to be a little easier if I show you exactly how it's done. So the way this works is we're going to create two models. We have one that we're going to train on just one feature, and another that we're going to train on all the features. And we're going to use cross-validation, and so we're going to add to an array the mean squared error and the R-squared score for each of those each time we go through. So we have 5 iterations. We go through, and for each one we get which one is our training and which one is our validation data. We train both of our models, the one on just one, this one on all the data, make our predictions for each model, and then for each model we calculate the mean squared error. And if you had gotten the notebooks a couple days ago and didn't update, this would be an assignment instead of appending. That was a mistake. You want to make sure that you are appending to this array the mean squared error and the R-squared score. Because what we do now is we take the average of the R-squared score for just one feature, and the average of the R-squared score for all of the features. And now we can compare those. And it is angry at me. Why are you angry? Because I didn't run previous one. Don't forget to run that one. There we go. So now that I've actually run this, those variables will exist. And it will tell me that using all the features still has a better mean squared error and R-square scored than using just one feature. So now we can do our final evaluation. The linear regression using all the features was the best, so we fit it to our entire training set, get our predictions on our test set, and then now we can take the mean squared error and R-squared score of the test set. And so our final R-squared score is 0.49 with a mean squared error of just over 3,000. And so there's a little side note down at the bottom that maybe I should have moved to the top, but if you want to be able to run the notebook the same way each time and not have to worry about partitioning them differently, and this could be because you want to go back later and make charts out of it, or you want to make sure that if you report it one way, you can go back and look at exactly why that might have happened. You can give train test split and k-fold a random state. And so then every time you run this function, it will divide it exactly the same way because you've given it that random seed. So that is it for linear regression, and that is actually it for regression type classifiers as a whole. So next we're going to be moving on to predicting a category instead of predicting a number, but I also want to take a very short break to see if there's any questions on regression and predicting continuous number labels before we move on. Okay, I know there's a little bit of lag in my video, but I don't see any questions, but always feel free, and I will notice them shortly. So if we go back, so because we're looking at a different type of classifier, we're also going to need a different data set. So the next one, I want to briefly look over the Iris data set. So a lot of this information we've already gone over. What's a data set? What's a feature? So the main point here is, what is this data set? Oh. Okay, so could you explain what the MSE and R-squared numbers are telling us? So MSE, the mean squared error, is on average, what is the squared distance between a point. I'm going to just go back. It's my nice little plot. Where'd you go? There we go. So mean squared error is on average, what is the square of the distance between a point and this line? So a small number means that all the points are clustered really close to this line. They're not very far away. And a larger number means you have more examples that are further from the line, and they're bringing that number up. The R-squared number is a quantitative measure from 0 to 1 of how well this line fits the data. I don't actually have how they calculate that handy, but it's trying to take something like the mean squared error. I might have... What did I say about that? Okay, so it's just trying to take that information and give you a 0 to 1 ranking so that you can kind of tell 0 means that there's no correlation. So if we had this line and our data was just a giant square filling up this entire plot, there'd be no real correlation because, it doesn't change as the body mass index increased, it's still all over the place. Whereas if it's 1, that means it's lined up perfectly with the line. If you have a lot of outliers, the MSE would be very high, right? Yes. So if you have a lot of outliers, the mean squared error would be much higher than if you have a lot of data that's, well, not outliers. And then there's a lot of different trade-offs to looking at different ways of measuring this type of error. So for example, you could have a lot of data really, really close to the line. So in general, it's a really good fit. But if you have one or two very, very far away, they're going to bring in, potentially a lot of penalty, even though, everything else is very close. So that's why there's different metrics. So you could do, instead of taking the squared error, you could just take the average absolute value of the distance. Different ways of looking at it. Does it make sense to remove outliers before training the model? Yes and no. So there's kind of different opinions on this, and it's going to depend on your data set. So on the one hand, if your data set tries to account for these outliers that don't happen very often, you could actually make it perform worse for most of your data because it's trying to fit these outliers when you'd have really good results if you just kind of ignored the outliers and didn't deal with them. The other way of looking at it is that outliers are real data. Like, even though it's very strange to have this and it doesn't happen often, it is an actual possibility, and so by getting rid of them, you're taking real data, away from your data set. So the answer is kind of yes and no, so it's going to depend on your data and what exactly you're trying to do. One compromise might be to take outliers out of your training set. So if you decide that you don't want your model to be biased by these outliers, you can take it out of your training set, as long as you leave them in your test set. And then, so the test set would still account for the fact that these outliers exist, and would penalize your algorithm accordingly. But for most data, it would perform better because it wasn't trying to skew to fit those outliers. So it really depends on your specific problem. Alright, so if there are no other questions on linear regression, oh no, we're good. So this iris data set, it's again available through scikit-learn, and so they have a bunch of explanations on it, but essentially we have 3 different species of this iris plant: setosa, versicolor, and virginica. And people have taken measurements of a lot of individual examples of these plants, and we're looking at the length and width of both the petals and the sepals. So this is on a primrose plant. It's pretty easy to see that the sepal's kind of this extra, not quite leaf behind the flower. It's a little harder to see on the irises. I think this might be the sepal and this is the petal, but I can't promise you that. I'm not that good at plants. But someone who knows a lot about plants has taken these measurements and measured the actual sepal and the petal of these plants. So we have 150 examples, 50 from each of these 3 species of plants. And then our features, as I mentioned, there's 4 of them: length and width of the petal, and then length and width of the sepal. And the biggest difference is that whereas before we were trying to predict a continuous number, now it's just the particular species of iris. So while it's still represented as a number, I believe it's 0, 1, and 2 for the 3 species of plants, they're not numbers in the sense that it makes sense to add or subtract or any of that. They're just labels representing setosa, versicolor, and virginica, these 3 species of plants. And so this is... okay, so we're importing our data sets, and pretty much everything else here is plotting related. So if you're interested in how these plots come about, you can check that out. Here again, we have the different keys. This is much easier to look at if we look at the first 5 examples. We have sepal length, sepal width, petal length, and petal width. But I'm just kind of going through this really quickly because we've already talked about most of this with a different data set. But here is a plot of sepal length versus sepal width, and we've got the label of the 3 different plants. So you can see one is kind of on its own over here. The other 2 are kind of intermixed. we're going to skip that. We can, of course, do the same things, the training and testing. Okay, so that's it for the Iris dataset. If you have any questions on this dataset, feel free to ask. But the next thing we're going to do is we're going to look at this KNN tutorial. Alright, so oops, put that water down. So KNN stands for K nearest neighbors. So it's a very simple form of supervised learning for classification. It's going to assign a label to any new input example based on the closest neighboring data points. And so this is going to be easiest to see by visualization. So a lot of setup. Here we're importing neighbors instead of the linear regression, but we still have our data sets and our training and testing splits. And then again, this is all just because I want to make the plot pretty. So we actually import our data set, which we've talked about already. And we want to make a plot. So here we're going to be plotting the sepal length and width. And it's the plot we've just looked at. So now let's talk about how we're going to train our nearest neighbors. So actually, here's a good place to go over this. So I said it's going to give it a label based on its nearest neighbors. So what it's going to do is, so say we have new sepal length and width. Let's say it is 7 and 3.5. So it would be right here. And so the way this would work is it would look at all these other points that are near this point. So we've got this one, maybe some of these. And so based on what those are labeled, it's going to give a label to this new data input. And so training it is very similar to with linear regression. Take your classifier. But the one difference is that when we create it, we can tell it how many neighbors we want to look at. And so I'd mentioned, finding the points that are nearest to it, and we can specify. We can say, only look at the one that's closest, or look at the 10 that's closest. So here we're going to look at the 15 closest neighbors, and we tell it that when we create our K nearest neighbors classifier. But then once we've created it, it has that same fit function. Okay, and so earlier I made x small is just 2 different features from our data set. And we give it our labels. And we can plot the classification boundaries. So all this is doing is for each point on the map, it's asking it for its prediction. So we've trained this classifier, and then we gave it a giant grid of every point on this map, and for each point we asked the classifier, what would you classify something here? What would you classify something here? What about in this point? We do it for this whole graph, and then we can get this nice colorized output that tells you where it would classify something as versicolor, this whole green area. This blue area is where you would call something virginica, and then over here is setosa, where it's all red. And so that's nice, and we can see how it would do. But we've got some interesting things going on. There's random splotches of green that wind up in here. And so there's 2 ways to look at it. Do you want to focus more on a couple that are really close? So for example, should this be green? Because there's a couple green ones in here. Would you want this random little circle to be green? Or do you think because most of the ones in that area are blue, it should be blue? And so this is going to reflect in how you choose the number of neighbors. So if we scroll down, what if we increase the number of neighbors to 30? So this is all basically the same code, but now we've said look at the 30 nearest neighbors, and now those little islands of green are gone because we're looking at more of the neighbors, and more of the neighbors over here are blue. Another possibility is maybe we do think that's important. Maybe this little pocket should be green and it should be blue, you know, here and here. Maybe those relationships are important. So you can also change your number of neighbors here, make that say 5. Run it again. And now you can see there's a lot, you know, there's more areas where something, you know, there's more little pockets where it's changed. So we want to make predictions, and we've got 2 samples. We're still looking at just the sepal length and width. So let's say we have, you know, some intern, and we say go out and measure these 2 plants. So they measure the sepal length and width of plants A and B, and then, so here we've put them into an array. We're going back to using 15 numbers. And we're training our classifier, and we want to know what those are. So our classifier says that plant A that our intern measured was Setosa, and plant B that our intern measured was Virginica. So if we want to plot those and maybe see why that happened. Alright, so that makes sense. A is clearly over here in this red area, and B is Virginica because it's over here in this blue area. But it's really close to the green area, and the 2 closest to it are both green. So maybe B really is versicolor and it's just classified wrong. So this goes back to choosing the number of neighbors. If we had used a smaller number of neighbors, it would have B would have been classified as green instead of blue. So it really depends on your, like I said, it depends on your data set and whether or not you think these small variations are important and how they're clustered. But another factor is that right now we're only looking at 2 features. Maybe the problem is that you can only tell so much from the sepal of this plant. Maybe the petal is really important and we should be including that. So tell our intern, actually, we want you to measure the petal length and width for these 2 plants as well. And then, so if we wanted to redo this, I would just grab this whole cell. And live coding is fun, but it should work. Alright, so I just copied the same code here. But the thing I want to change is... Okay. So where do I define x small? It's way up. There we go. I also want to grab this. Okay. So instead of the first 2, we take the last 2 features because now we want the petal length and width. And because we're still using x small, we should be able to reuse a lot of this code. And most of this is just plotting. And oh, we're going to need to re-specify A and B as well. So if we go up here and just steal this code as well. Okay, so plant A, we want to switch to petal, so that is 1.5, 0.5, and plant B, 4.8, 1.5. So let's see if this works. Alright, there we go. So we've plotted our new data, now we're looking at petals, and we can see A is still red. If you remember, A was red before, and it's even more clustered. So this Setosa plant is really easy to pick out. But B is now classified as versicolor. It's green over in here. And you can see that this is, it really doesn't want to classify anything as blue here. So this is probably using maybe too many. Oh, we never. That's a good point. We need to retrain our classifier. Here we go. Okay. So now we should be good. We have our new data looking at the petals. New example also looking at the petals. We retrain our classifier, and then we plot the results. There. Now this makes much more sense. So B is still classified as green versicolor. A is still red. But so you can see, looking at the petals, we get a little bit of a better distinction. This line, there's more of a difference between the green versicolor and the blue virginica. So that's part of why it's important to consider as many features as you can, because sometimes one will have more information that another doesn't. Another thing we can do, so we talked about the number of neighbors, but we can also tell it to take distance into account when looking at the neighbors. So before, if we told it 15, it would just take the 15 that are closest to B and pick the label that got the most votes. But now, if we tell it to use the distance metric, it would look at the first 15, but it would weight their vote by how close they are. So these that are really close would get a higher vote, and these that are further away, even though they're included, would have a much smaller vote. So this is one way that you can include data from more examples without worrying too much about the data being far away and not relevant, because as it gets farther away from what you're looking at, it'll have less of an impact. So if we look at this here, so we're still looking at just the petals. Yes, so we're still looking at just the petals because I changed that in our last example. But again, it doesn't change their actual evaluation, but it will change these lines a little bit. And we're going to skip this section. And like before, we're going to move on to actually using all 4 features at once. So this is exactly what we've been doing before, except our examples now have 4 features each. We're using 15 neighbors. We create our classifier using those 15 neighbors. We tell it we want to consider the distance when we do this. And then we get our predicted labels. And so considering all 4 at once, it says that A is still setosa, that has never changed, and that B is versicolor, which I believe is the green. Yes, which is that green. So we've looked a little bit about how k-nearest neighbors works, and if there are any questions, you know, by all means ask them in the chat. But so we can evaluate this very similarly to what we did with linear regression. But the main distance, so we split it into training and test, get our number of neighbors, we fit on the training, and then we can get predictions on the test. But unlike with regression, a mean squared error doesn't really make as much sense. We're not plotting a line. But what we can do is check the accuracy. So the accuracy is the percentage of the time it got it right. So how many times did the prediction equal the actual label? And so we can do this, and it has really good accuracy. It is, 93.33% accurate according to this. And like before, if we want to compare multiple models, we can do cross-validation. So here, we can look at all these different numbers of neighbors, 1, 3, 5, all the way up to 40. And so we do a very similar thing, except we make a dictionary to hold all of our lists, where the key is just the number of neighbors that we're looking at, and then it keeps this list that we're going to append to. But like before, we're going to do 5 folds. We get our training features and labels, our validation features and labels. And then for each fold, we want to go through all of the classifiers that we're evaluating. We create that classifier with that number of weights using the distance metric, train or fit, predict it, and store those accuracies. And then to select a model, we want to look at what is the accuracy for each of these. So a lot of them are really similar. We have a lot that are about 98% accurate. And so this is where things get a little interesting. So according to our validation data, we can pick any of the k equals 1, 5, or 10, because they all have the same accuracy. So there are different methods you could use to try and figure out which one you want, but one way is to assume that simpler is better. So we could say that k equals 1 is the best because it is the simplest model. So if we went for that, and so here, so last time I ran this, k equals 3 gave me the better accuracy, but I mentioned before that how it's randomly partitioned will change things. So here I decided that I want to use 1, so I'll change that. Then if I run it, it tells me that it gives me a final accuracy. But you could also have decided to choose 5 as kind of a compromise. It is not the most complex, but it's not overly simple if you're trying to avoid both overfitting and underfitting. We won't go too much into that right now, but I believe for any of those cases, because they all got such high accuracy, any of those would be a pretty reasonable selection. Here's another note on that randomness. And so that is it for k nearest neighbors. The next thing I want to do is a kind of more popular and common classification method called support vector machines. But while I'm switching over, again, if there's any questions, be happy to answer them. But we're going to go, and the new notebook is SVM tutorial. Alright, so I don't see any questions. Hope the chat is still live. It's turned dark. Okay. So, support vector machines are also doing classification. So we're also going to be looking at this iris dataset. But they are trying, instead of grouping things based on their neighbors, they're trying to define a boundary that's going to maximize how far apart these classes are. And so the easiest way to see that is with an image. So this is just kind of a simplified data set, but if we have two classes that can be perfectly separated, you can draw a line between them and all from class A are on one side and class B are on the other side. It's trying to draw this line so that the distance between the nearest point and the line is as far as possible. And so we have these dotted lines that are going through, that are parallel to our dividing line, but go through the points on either class, on either side, that are closest to it. And so what this is saying is that this line, for at all points, keeps the two classes as far apart as possible. So if we went through at maybe a more steep angle, we could still separate the classes perfectly, but we would be getting pretty close to this point here, and pretty close to these points down here. So that's why So that's why I picked this, this line, because if you bring this side up and this side down, you'll be getting farther and farther away from those closest points until it finds the best place to put this line. So to get started, again, there's a lot of plotting information. The new line is that we want SVC. This is how we import support vector machines from scikit-learn. We import our dataset, which we've already talked about. We can plot the data, but we've really already talked about this. So when we create our support vector machine classifier, we have a kernel, which we'll talk about later, but right now we're just going to call it linear, and decision function, which you can also ignore for right now. But so we create this classifier, and again, it has this fit function. And after we've created it, we can see that it has all these internal parameters that, again, we don't have to worry about right now. But what could be interesting to look at is these classification boundaries. So you can see it looks a little bit like k-nearest neighbors, except it's got these straight lines. And there's no little segments of, you know, this little spot's going to be blue or this little spot's going to be green, because it's not relying on the neighbors. It's creating these perfectly straight lines to try and separate our data. And so if we want to look at some predictions, we have our new plants A and B again. And we plot them. And there we are, plant A and plant B, and support vector machines put plant B firmly in the green versicolor. So I was talking about these support vector machines and trying to, you know, separate the two classes, but where are they in this example? So in our toy, everything was perfectly separable, but here, the only thing that really is this red Setosa plant. The other two, you can't separate them perfectly with a line. There's no straight line that will split green from blue. So how does our classifier handle that? This is just, this is a function for plotting help. Just run that. And here is our lovely messy plot. So it's a lot more cluttered than in that toy example. But we can see, so those thick black lines go along these three decision boundaries. So these are those decision boundaries we talked about before. And then these dotted lines are the ones that go through, they're called support vectors. And these are, if it were perfectly separable, these would be the closest to the line that don't actually go over it. But here we're using different penalty parameters to penalize points for being too close. You don't really have to, you know, don't worry about it if you just think this is a cluttered mess. I also just think this looks like a cluttered mess. But the point is that it is applying this same idea of trying to find this nice separating line. And it has a way of trying to find that line even if our data can't be separated so nicely. Okay, so one of the things I mentioned earlier that you didn't have to pay attention to right now is there is a kernel that you can specify when creating this classifier. So this is going to determine how it splits the data. So before it was linear and it created these straight lines. There's another kernel called the radial basis function, or RBF, and this is going to make more curved lines. So when we train our new classifier with that kernel and plot it, you can see how there's more of a curve to these lines. So it's very similar classification boundaries, but now instead of being completely straight, they can curve. And so if we plot the actual boundaries, so this is why it's curved. It's because instead of making a straight line, we've got these circles as decision boundaries, or not really circles, but ovals or ellipsoids. And so this is even more of a confusing mess than before, but the main point is that instead of using a straight line to separate things, we're looking at circles, sort of like on a topographic map. There are other kernels that exist, like polynomial and sigmoid, and so that's one of the reasons support vector machines are popular, is that different data types will tend to group themselves differently. So some are best classified by separating them with a line, but others tend to group in kind of circular clusters that maybe a line can't quite separate, but drawing circles could. So they're transforming your data, or the predicting line, into something that's that fits a little better to your data. And so I know support vector machines are a little strange, so if anyone has any questions, again, feel free to ask them on our help chat. So we've already looked at, things that happen when you use more than two features. So we're going to combine that with evaluating our classifier. So we split it into training and testing again. Quickly look at our accuracy. Pretty good accuracy. But the really interesting part is we want to compare linear and radial basis function kernels. So we're doing something very similar that we did with k-nearest neighbors. We're storing our accuracies in a dictionary, doing cross-validation to get the validation accuracy. And so, in our case, the linear actually works better. The linear kernel works better than the radial basis function kernel. So, we take a classifier with a linear kernel, fit it in our training data, test on our testing data, and we find that our model is almost 98% accuracy. It is almost 98% accurate. So it's really good at, yeah, so this is a pretty easy data set to separate. K-nearest neighbors and support vector machines worked really, really well on it. But that is it for support vector machines and classification in general. I have one more notebook to go over on clustering as opposed to classifying, so when you don't have labels for your data. But as usual, if there's any questions as I switch over notebooks. Oh, here we go. How do you decide what kind of classifier to use for what kind of data? Or do you just run them all and pick the one with the best accuracy? So a little of both. So there's different types of classifiers that work better for different data. So the biggest category is what are you trying to predict? So if it's a continuous number, like house pricing or that diabetes metric, you would pick something that predicts a continuous number, like linear regression. If you're trying to predict a label, like type of plant, or identifying something in an image, whether there's a dog or a cat, you would pick something that does classification. But within those, there's a lot of different classifiers that you could use, and so it's going to depend on how complicated your data is and what model kind of fits those complexities best. So usually you rule out the obvious ones by hand. So I'm using the Iris dataset, so I would rule out linear regression, and I would probably roll out some of the super complicated ones like neural networks and figure those are too complicated. So I might look at support vector machines, k-nearest neighbors, maybe one or two other options that also do classification, but then yeah, I would run them all on validation data and probably pick the one that works best. Okay, so as long as there's no more questions on classification, the next one we're going to do is, it's called K-means tutorial. Okay, so this is getting a little interesting. This is where we're going to assume that you don't have labels for your data. So at the very beginning I mentioned you might use clustering for examples where you've taken a lot of pictures, you download them off your camera, and you've never told the computer, like, this is a picture of me, or this is my cat, or my parents, but you want it to group these pictures somehow, and just kind of see what kind of groupings it can come up with, find similarities between them. This is, the picture example is kind of a good one because there's just so many pictures out there. But if you just downloaded everything from Google Images, like they've tried to label most, but people have to actually go and do that. So you can also just try and find similarities between images. So it's called unsupervised learning because you don't know the labels. And so when we import it, we're going to import k-means from scikit-learn's cluster. And then we import our data sets and a lot of lines just, again, to make the graphs pretty. Import our iris data set. We've already looked at that. So here's that plot we've been looking through before. But as I mentioned, when we use k-means, we don't use these labels. Usually we would be using this with data that doesn't have labels. But we can also just not give it the labels. And so this is what it's going to see. So we know that these are the labels and these are how the plants are laid out. But when we give it to k-means, this is all it's going to be able to see, is this arrangement of dots. And so if you were looking at just this, how might you group them? I mean, I might say that there's one group here and one group here. So if we didn't know that there were actually 3 plants, we might do that. If someone told us, no, there's 3 groups, just looking at it, I might go 1, 2, 3. Maybe say this is kind of a dividing line here. So that's essentially what k-means is going to do. We're going to tell it how many groups there are, or how many groups we think there are, and it's going to try and make those clusters. So you choose your number of clusters. And so we're telling it 3 because we know that there are 3 species of plants. But in the real world, we wouldn't have these labels, so we might know that. We might know that there are 3 species of iris, and we just don't know which ones in particular are in these images. Or we might have an educated guess. We have a bunch of pictures of dogs, and we think that there are probably 10 types of dogs. We would, so we'd make our best guess at how many clusters, but this is another thing that you might go through several iterations and see how it groups them when you give it different numbers of groups. But so for right now, we're going to give it 3. We're going to create our k-means object, and we're going to fit. And so this is essentially the same fit that we've been using for all of our algorithms, except here we're only giving it the feature data. There's no labels. And so if we plot it, what this is showing us is the 3 divisions that it found. And it's also showing us the mean, or what it considers to be the centroid of that data. So this one makes the most sense. You know, there's all this data that's been grouped in here, and you can kind of see that this is kind of the center of that data. And you can see it here too. For all this data that's in the very dark color, this is about the center. And then of all the data that was put in the gray, this is about the center of those data points. But again, it's plotted in gray because it doesn't know what the classes are. But interestingly, it does kind of follow the classification lines that those k-nearest neighbors and support vector machines found. So even though it doesn't have any label information, it was able to make some decent clusterings. Yeah, exactly. Someone pointed out that it looks similar to SVM. And so even though it doesn't know what the actual boundaries are, it still found very similar boundaries because we were giving it the same number of classes. So if we gave it, so if we go back up here and say we want 5 clusters, we would get something quite different. So here, it looks a lot less like the support vector machine, because it's tried to find 5 clusters in this data. And so it's done some really interesting boundaries here. And the colors aren't quite right, because I only gave it enough options for, I believe, 3 or 4. But these are the 5 different centers it found. If we go fix this, because we know it wants to be 3. And so we can kind of cheat and put our labels back in because we know what they are. But, you know, as was already pointed out, it did a very similar boundary to what support vector machines did. And so here is just, okay. So if I'd used this expanded color map, it would have shown better. We can do that down here just for fun. So if we want to look at more clusters, we would want to use this color map. We have another question. If the choice of best model depends on the random partitioning of the data, do people rerun multiple times, and how many times? That's also a really good question. So yes and no. So if you run your analysis many times until you get one that works well, you can just go with that. So say I ran my last notebook, 5 times and found the best accuracy that I ever get with the support vector machine. If I said that's how accurate they were, that would be a poor representation of how that algorithm actually works. So the important part about evaluating your data set is you're not actually interested in getting the best score on our test set. We want to find the algorithm that does best on the real world data that we're eventually going to use this classifier for. So if I were a scientist and I wanted to actually train this algorithm so that people could take pictures of an iris or take measurements from an iris and send it to my classifier, and it would tell you which one it is. And that's what we're really interested in. We want it to work well on that data. So if we keep rerunning it to find one that works well on a partition of our data, we're over-promising. We're overconfident about how well this is going to work, whereas in reality, it probably wouldn't work quite that well. So this is why, or at least one part of the reason that k-folds is really popular. So you can go over and get kind of an average. And another good thing to look at is not just the average accuracy, but if you also look at the variance or standard deviation that you get from running that. So like how different is it between folds? And if you get a lot of variance between the folds, like in one you get 90% accuracy, another is 60, and another is 100, you want to be a little more cautious because you know that how well your classifier is performing is depending on how well or how your data is distributed. Whereas if you were to run it several times and it's all about like 95, 96, 94, you could be a lot more confident that it doesn't matter how my data is partitioned. So I hope that explanation made sense, but in general, you want to, it is often good to run it, multiple times, but you want to take an overall look at an average. You never want to run it multiple times and pick the best, but running it multiple times and taking statistics on it and saying, on average, we get an accuracy of this, but, there's this much standard deviation. That's a much safer way of doing it. And then another question, and k-means, how do we know that the cluster centroids are not moving? And when should we stop repeating steps 2 and 3? Alright, so I will bring this up. Where did I put that? Okay, so what they're talking about is there's 3 steps in training your classifier. You pick how many groups you want, which is the first thing you do. You assign each data point to the group with the... okay, so you tell me how many groups you want and pick random centroids, or center points. So those were the X's that I pointed out. And then in step 2, you assign each data point to the group that it's closest to. And then for the third, you find the average value of each feature in the center point, assign that cluster, and then this is the new centroid. So always better with visuals. So go back down. Okay, so this was the final step, but it would still apply here. So we have these 3 centroids, and I'm going to take a mini segue. So there's another comment. So basically, all machine learning algorithms are doing is trying to identify patterns in data. And yes, that is exactly what they're trying to do. Find useful patterns and then tell us about them and make useful decisions. So in k-means, we're trying to find where is our data grouped or clustered. So we have this center point. And so for each point in our data set, we would decide which center point it's closest to. So, all of these are closest to this one. They'd be assigned to medium gray. And all of these that are closest to dark gray would get assigned to this one and light gray. And then you would you would find the center point of this data. So, in the x direction and y direction, where's the center point of all of the data assigned to medium gray? And you would just do the same for dark gray and light gray. And then you would move this center point to that new location and do it again. And so when you stop is when you define some kind of a tolerance. So when this stops moving at all or stops moving very far, you can figure that, you've found the center point. If, every time you run it, your center point is staying about the same, that means that when you run it again, your data is continually being assigned to the cluster it's already in. Nothing is changing. And so when it's not moving much, that's when the algorithm stops. And so when we created our k-means object, it printed out a bunch of information about it. We have, is there a tolerance? Okay, so we have a tolerance, which I believe that is the minimum movement. So if it moves more than this tolerance level, it'll stop. Another option is there's also a max number of iterations. So if it hasn't stopped moving around, but you've hit 300 runs, you can also tell it to stop. So there's two ways to stop k-means. It's either when that center point stops moving around, or after you've tried a certain number of times, you can just say stop. You might never find it. So either one works. Okay, the question is, how do we code it? Can you please show that in the code? Sure. So because we're using scikit-learn, where are you? So all of that actually goes into this fit method. So everything scikit-learn does, all that iterating and looping through, that's part of this fit method. So scikit-learn has some information on all the... Yeah, okay, so tolerance is a measure of how much it can move. But so you've got kind of all this information about how scikit-learn does it, and if you wanted, you could get into, where would you go for that? Do you have to download it from GitHub? I wonder. There we go. Okay, so if you want to know how to code this, let me go over how to get there again. So in this k-means tutorial, I clicked on the k-means function. There's a link here. It took me to scikit-learn. They have a page about information on how you would use that. And then at the very top here, it's talking about the class k-means, and there's a source. So I clicked on the link to source, and here's the actual code that scikit-learn is using to create k-means. This is all commentary. Okay, so it's got an init function. Some things are, they've got some checks. Okay, here's fit. This is what we want. So it looks like here we're assigning the cluster centers, their labels, and all this different information. Where is this? K-means. Okay, so fully explaining this would involve digging into code that I don't know where they define what they're actually doing. Where are you doing this? Oh, maybe this is what we want. Okay, so if you scroll down far enough, you'll get to mini batch step, which is, they call it the incremental update of the centers for the k-means. So there's a lot of functions telling you what it's doing. But it looks like it's, you know, if we're reassigning it, we go through, here we go. So we're picking new clusters among the observations. Something about sparsity. And then we find, yes. So find the points that are assigned to the center point. If we haven't hit our maximum count yet, we're finding this difference. So how far is each point from the center point? And I believe this should be finding and updating these center points. So this is all scikit-learn's code. If you really want to dig into exactly how that works, you could dig through there. There's also tutorials on the internet that will actually explain how k-means works in a more conceptual method and with more, because this isn't really meant to be read through, this is meant to be run quickly and efficiently. But I can, after this tutorial, I can try and find some links and I'll throw them into this chat if anyone's interested. But yeah, that's about as much of a deep dive I can do into scikit-learn right now. But I will definitely look for those links for you. And if you ever don't find them, just find me on Twitter and say, hey, remember those links? Could you post them? And I will do that too. Alright, another question. With some machine learning algorithms, I've seen some predictions come with a confidence percentage. Is there anything like this here that could say, hey, this is very close to the divider line, so I'm only like 25% sure? That's a really good question. So it's going to depend on your algorithm and how it's implemented. Can k-means do that? I know that support vector machines have, let me go back to SVMs. So I'm going to insert a new cell below. I believe it's predict proba. No, what is it called? Ah, okay. So okay, there we go. So what I did was when I create my classifier, so I'm back in the SVM tutorial. And so when I create my SVM classifier, you know, I give it the kernel. I also say probability equals true. This tells it that we're going to want these probabilities that say, you know, how sure are you of a different point? So once we've done that, train it that way, we can say predict proba for predict probabilities. And so now, instead of giving you an actual number, it's going to give you 3 numbers. And so each of these is a measure of how confident it is in each one. So they're not quite probabilities. If I do... Okay, let's make sure I do this right before I try and explain it. First row. Oh, need to actually print that off. So if I just do this. No, my math's not quite right. Okay, we'll just not do that. Okay, so I'm not the greatest at live coding, but so if you predict probabilities, it's going to give you, oh, now it is a probability. What did I do? Oh, you know what? It probably was just giving strange numbers when it was a full array so that the data would fit. Yeah, that was it. Okay. So all along it was already actual probabilities. But you can see it is almost completely sure that this example belongs to group 3. It doesn't think that it belongs to group 1 or 2. It's a very low probability. So most of the ones that can do something like this will have something along the lines of a predict proba or predict probability function in scikit-learn. So if you're interested in doing that for your scenario, you could always check and see if that's implemented, and that's a really easy way to get those probabilities. And then use that information, you know, to decide how sure you are about this decision. All right, where was I? There we go, scikit-learn k-means. All right, so we were just talking about how actually it works and how it keeps moving that cluster back to the center. And where did I stop? Okay. And then, I don't think we need to do this. We've already looked at this. But yeah, so giving it different numbers of clusters is going to tell k-means to map it to different, you know, make different maps, make different decisions, cluster it into smaller and smaller groups. So we can still predict. So although, yeah, so it can still predict. I believe that's just a predict function, right? Yeah. So it still has a predict function. So even though it doesn't have labels, once it's trained, it has these clusters. And so it can predict which cluster something belongs into. So we have, you know, these two new plants again, A and B. A belongs to cluster 0 and B belongs to cluster 2. And because we've worked with this before, we know that A is the red Certosa and B is the green Virginica, I think. We can do this again using different features, but that is k-means in a nutshell. So that is actually all of the notebooks I have to go through. I have one more thing on here. Okay, so I'll also give you a link. I'm gonna write down, let's see, slides and k-means. Okay, so I'll give you a link to these slides also, because I have some additional resources if you want to learn more. So these are all actually links, but there's scikit-learn has a lot of documentation. There's a website called Neural Networks and Deep Learning, so if that's particularly what you're interested in, want to go into neural networks, I thought that was a great explanation. Pythonprogramming.net also has a online tutorial at scikit-learn that you could look into and try and learn some more. You can also take Coursera courses. There's one by Andrew Ng at Stanford that I enjoyed. It's very math-based, and he has a newer one that I think, so this uses Octave, and I think the newer one uses Python. But this is very academic and math-based, whereas I've had a lot of people recommend this University of Washington Coursera course as something that's more practical-based, how you would use it. So depending on what you're looking for, either one of those is I would recommend. Johns Hopkins also has a series on, it's more data science based and it uses R, but it's still got a lot of like really good information on working with data and data analysis. I think, yeah, okay. So that is it for my actual presentation, but I am definitely happy to answer any remaining questions you might have, and I will get the links to the slides and find some information on k-means for you. Here's the link to my slides. And thank you all so much for coming. I really hope you enjoyed it. And awesome, thank you. And yeah, I definitely reach out to me if you have any questions. I love talking about machine learning. I'm really excited about it. So, you know, don't be shy. If you have a question on anything, let me know. And I'll just give it 1 or 2 more minutes in case there's any questions that I can answer by speaking, and then I'll hang out in the help chat for a while. Can we download? I think you can download the slides. So that link should get you there. Let's see what happens when I go there. If I wanted to download these, I needed to load the page first. Oh, someone is answering in the chat. Awesome. Alright, well, I'm going to end the video, but like I said, I'll get you all those links and hang out in the chat. Thank you all so much for coming.